is Sunday, January 25th. I have a meeting before lunch around noon, a little bit before noon. So I wanted to just hop on and get a short reading session in. I'm not going to hit my 100 pages today because I just don't have the time. I have that meeting, and I also wanted to get some stuff done off stream. Like last night, someone was asking for me to create a Discord, and I feel like now that I gotten like some streams under my belt here, I want to do some work to improve the quality and discoverability of the stream. So I'm gonna do that probably this afternoon after lunch. So I'm gonna be taking a very long lunch because I have that meeting. I have cardio and I have this off stream work. So I figured I'll do the short stream this morning before lunch, break for lunch, and then come back maybe for another short stream this evening. So I'm not looking to get 100 pages done. And then the other thing I wanted to do with these streams moving forward, since we're getting towards the back of the book, we're definitely on the back third here. Actually, I don't even know if we're technically on the back third, but let me do one thing here. So if I look here, it still says I'm on chapter TN. I'll do T. I'm already on chapter 43, so this would be 16, 7 to 16. Done. So all, yeah. And then if I do T, I'm on chapter. Okay. So now it says 64. So almost 2/3 of the way in. Not technically on the back third, but pretty much. So now that I'm on the back third, these chapters are actually really meaningful to me because they contained subjects that I have only tangentially encountered in my career, and I want to spend a little bit more time fully understanding and writing test programs and doing more experimentation. I feel like the first third especially, like there wasn't really like the need for me to do a lot of experimentation because there's a lot of review. The second third, I was like going really fast trying to get through the book, so I didn't really take any time to do any exercises. But this back third, I feel like I want to do more experimentation and more exercises, which is going to require me to slow down, not just to do the exercises, but also to just like take my time with the material so I feel motivated to experiment. So what I've noticed is when I set this goal of 100 pages a day, basically that goal kind of like led to me not being motivated to do a lot of experiments, which I think is going to require me to slow down my reading, take time to do experiments, be happy with not even hitting half of my target, because otherwise it's just going to be a grind. And if we look at the calendar, like my goal was to have it done by Thursday if I read 100 pages a day. I could still do that. It's going to be a brutal couple days though, and I feel like I won't have learned as much if I just took another couple days to get through it, you know? So I have say I do until end of the month. I did want to finish before the end of the month, so I have until Saturday technically. So that'd be 1, 2, 3, 4, 5, 6, 7. I have 7 days. And then if I do, let's see, I'm on page 877. So 1400 minus 877. That includes all the appendices, by the way. So there are some appendices I do want to go into. Like Appendix A was about S-trace. It's very short, but I did want to do that. And then I don't know what the other appendices are about. Let's check them out here. This one I read, but that was kind of like a waste of time. I don't know why I did that. This would be interesting. Kernel configuration, that'd be interesting. These are not necessarily things that I have to eagerly read, but tracing systems calls, definitely going to read that. Just a couple of pages. Casting the null pointer, same thing. Kernel config, same thing. This thing was a waste of time because, I mean, I was familiar with getopt, which is I think the library function that they use here. Yeah, I was already familiar with it, and I was hoping I would develop by reading this, I would develop like an intuition for like using it in a way that would speed up my specification of arguments for programs that I write. But really, I always just come back to just like doing some like janky like positional stuff with argv. It's just so much simpler to implement than like setting up like all this stuff and then reading the args. It's just like, it's a very heavyweight API that I don't really like feel is necessary for especially toy programs. And he does the same thing in the book. Like, he doesn't use GitHub for stuff in the book. So yeah, that's where I'm at this morning. I figured hop on. It's 9:21 right now, so let's get out of here. Actually, my bad. I was going to take that and divide it by 7, see how many pages. So that's like 75 pages a day if I wanted to finish by the end of day Saturday. And then also Friday I have some like social stuff I'm doing, so I'm not gonna be able to like stream the entire day on Friday. So yeah, I guess I just gotta get really aggressive about starting early, staying focused. If I want to finish on time, that's what I'm getting here. If this was 5, oh, sorry, wrong expression. Do that. So yeah, even at right now, if I was to finish by end of day Thursday, then I would have to read 100 pages, still over 100 pages, because I had to I wasn't able to read 100 pages yesterday. So if I look here, 1400 is, yeah, it does not include the appendices. Yeah, so I even have more than that. It's a lot. It's a lot to do in a short period of time, so let's get started. No sense in waiting around here. All right, chapter 43, IPC, Interprocess Communication Overview. This chapter presents a brief overview of the facilities that processes and threads can use to communicate with one another and to synchronize their actions. The following chapter provides more details about these facilities. The following chapters provide more details. A taxonomy of IPC facilities. Figure 43.1, which is on the next page here, summarizes the rich variety of Unix communication and synchronization facilities, dividing them. Actually, sorry, I need to start the clock here. So it is 8:77, and we are starting at 9:24, which is 1 minute earlier than we started yesterday. So we're still making progress at starting earlier. All right. So dividing these facilities into 3 broad functional categories. Communication. These facilities are concerned with exchanging data between processes. Synchronization. These facilities are concerned with synchronizing the actions of processes or threads, signals. Although signals are intended primarily for other purposes, they can be used as a synchronization technique in certain circumstances. More rarely, signals can be used as a communication technique. The signal number itself is a form of information, and real-time signals can be accompanied by associated data, an integer, or a pointer. Signals are described in detail in chapters 20. Yeah, okay, we don't need to go back to signals. Although some of these facilities are concerned with synchronization, the general term interprocess communication is often used to describe them all. Okay. So we got communication. So shared memory and data transfer. Data transfer can be in the form of byte stream, pipe, FIFO. Hold on a second. Sorry, I just had a sneeze attack. So byte streams are things like pipes, FIFOs, socket stream socket, pseudo terminals. Messages are system V message queue, POSIX message queue, and datagram socket. So stream socket might be like a TCP, and then datagram would be like UDP. Shared memory. System V shared memory, POSIX shared memory, and memory mapping, anonymous mapping, and map file. I'm most familiar, and that's not saying much, but I'm most familiar with the memory mapping stuff. System V and POSIX shared memory I'm not as familiar with. Signals, standard real-time signals, we're already well familiar with those. Synchronization, things like semaphores, which are in two varieties, System V and POSIX. POSIX has named and unnamed. Then there's file locking, a record lock, FCNTL, and a file lock, which is a flock. I was always curious about these calls ever since like 2011. I knew these things existed, but or 2010 really. I knew these things existed, but I never really used them. I would use the directories itself or files themselves as locks, because you can do atomic operations with the creation of files, and you can basically implement your own locks at the like higher level. So I'm curious what these like specific file locking capabilities provide over just like, you know, creating a directory and deleting the directory atomically. Mutex threads, so these things like futexes, I guess. Conditional variable threads, we already talked about those. And they can be shared between processes if you memory map them, I believe. So that's why they're saying that they're, or no, they're just saying that they're used in threads. That's what this is in parentheses. But I remember reading that you could share them if you do memory mapping. So they might be able to be used in that way between two separate processes. One thing I'm curious about, Unix domain sockets. Where would they fall in this taxonomy here? Let's open up a little thing here and say, what type of communication mechanism are Unix domain sockets? Socket-based apps using the OS networking API, but confined to the same host. I think either pipes or sockets here might be the taxonomy that they fall under. Hopefully we get to those at some point. But I don't see an explicit call out for them. So if it's not these socket types, then, or the pipes, then it might be something else. As figure 43.1 illustrates, often several facilities provide similar IPC functionality. There are a couple of reasons for this. Similar facilities evolved on different Unix variants and later came to be ported to other Unix systems. For example, FIFOs were developed on System V, while stream sockets were developed on BSD. New facilities have been developed to address design deficiencies in similar earlier facilities. For example, the POSIX IPC facilities, message queues, semaphores, and shared memory were designed as an improvement over the older System V IPC facilities. In some cases, facilities that are grouped together in figure 43.1 actually provide significant different functionality. For example, stream sockets can be used to communicate over a network, while FIFOs can be used only for communication between processes on the same machine. Communication facilities. The various communication facilities shown in figure 43.1 allow process 2. My monitor is glitching out so much this morning. Move the thing back there. Where do I leave off here? Okay, so the various communication facilities shown in figure 43.1 allow process to exchange data with one another. These facilities can also be used to exchange data between threads of a single process, but is seldom necessary since threads can exchange information via shared global variables and mutex regarding their access. We can break the communication facilities into two categories: data transfer facilities and shared memory. So shared memory generally is more performant, I would say, whereas data transfer, you're making copies. So data transfer will be more safe, but it involves a lot more copying and a lot more machinery to move data around. Whereas shared memory, you're literally just like putting the data into memory and then reading the data from memory, and have some like mechanisms to coordinate access to it. So data transfer facilities, the key factor distinguishing these facilities is the notion of writing and reading. In order to communicate, one process writes data to the IPC facility, another process reads the data. These facilities require two data transfers between user memory and kernel memory, exactly. One transfer from user memory to kernel memory during writing, another transfer from kernel memory to user memory during reading. Figure 43.2 shows the situation for a pipe. Shared memory. Shared memory allows processes to exchange information by placing it in a region of memory that is shared between the processes. The kernel accomplishes by making page tables. Entries in each process point to the same pages of RAM, as shown in figure 49.2 on page 1026. I'm just going to pull that up here. 1026. That's way far ahead in here. Okay. Yeah. So this is in chapter 49, memory mapping. I guess I can pull that up here as well. Just going to duplicate, so then we'll just go down to page, what is this, 1026. It should be about here. There we go. 1026, this diagram here. So we got page table entries for map region and process A and process B. They both map onto physical memory. That is the same physical memory. And then I/O is managed by the kernel to take that memory, and when you do memory mapped I/O, it'll take that memory and put it into the file. All right. A process can make data available to other processes by placing it in a shared memory region, because communication doesn't require system calls or data transfer between user memory and kernel memory. Shared memory can provide very fast communication. We can further break data transfer facilities into the following subcategories: byte stream. The data exchanges via the data exchanged via pipes, FIFOs, and stream sockets is an undelimited byte stream. Each read operation may read an arbitrary number of bytes from the IPC facility, regardless of the size of blocks written by the writer. This model mirrors the traditional Unix file as a sequence of bytes model. Message is like datagram type things. The data exchange via system v message queues, POSIX message queues, and datagram sockets take the form of delimited messages. Each read operation reads a whole message as written by the writer process. It is not possible to read part of a message, leaving the remainder of the IPC facility. Nor is it possible to read multiple messages in a single read operation. Okay. Pseudo terminals. So a pseudo terminal is a communication facility intended for use in specialized situations. We provide more details in chapter 64. A few general features distinguish data transfer facilities from shared memory. Although a data transfer facility may have multiple readers, reads are destructive. Although a data transfer facility may have multiple readers, reads are destructive. A read operation consumes data, and that data is not available to any other process. The message peak flag can be used to perform a non-destructive read from a socket. UDP sockets allow a single message to be broadcast or multicast to multiple recipients. Synchronization between the reader and writer process is automatic. If a reader attempts to fetch data from a data transfer facility that currently has no data, then by default the read operation will block until some process writes the data to the facility. Shared memory. Most modern Unix systems provide three flavors of shared memory: System V shared memory, POSIX shared memory, and memory mappings. We consider differences between them when describing the facilities in later chapters. Note the following general points about shared memory. Although shared memory provides fast communication, the speed advantage is often offset by the need to synchronize operations on the shared memory. For example, one process should not attempt to access a data structure in the shared memory while another process is updating it. A semaphore is the usual synchronization method used with shared memory. Data placed in shared memory is visible to all of the processes that share that memory. This contrasts with the destructive read semantics described above for data transfer facilities. I think this depends on like the visibility of the writes. Like sometimes like a CPU will be writing into its cache, like its local cache, and like it won't actually flush out to main memory, and so it's not visible to other cores. I guess it depends on the cache coherency between the different cores, but I remember learning it when I read about Java concurrency that depends on the memory model and the architecture that you're on. But just because you do a write to memory doesn't make it visible necessarily to all of the processes immediately. There might be some like eventual consistency, and some process architectures don't even have cache coherency at all. So yeah, you'll be entirely dependent on when the cache gets flushed out to main memory. Synchronization facilities. The synchronization facilities shown in figure 43.1 allow a process to coordinate their actions. Synchronization allows processes to avoid doing things such as simultaneously updating a shared memory region or the same part of the file. Without synchronization, such simultaneous updates could cause an application to produce incorrect results. Unix systems provide the following synchronization facilities: semaphores, file locks, mutexes, and condition variables. Semaphores. Semaphore is a kernel. So semaphore, my understanding, because I've only used them a handful of times, But semaphores like are literally the flags that people use when they're signaling in real life. But in computing, semaphores, I've only encountered them implemented in user space. I've never encountered the kernel semaphores. But generally, it's like you have multiple things waiting on a signal, and then, well, I guess it's the way I would explain it is kind of like a mutex, where you can have multiple things acquiring a lock. So the semaphore will have a capacity or a size or a length, where it'll be like, say, a size of 10, and say you have like 100 concurrent threads trying to gain access to the semaphore. Only 10 will be allowed to have access at any given time. And when one of those 10, returns, unlocks its aspect of the semaphore, then another one of the other 90 that are waiting can acquire it. And because of that, it's kind of like a mutex that allows for multiple concurrent actors to acquire it up to a certain amount. That is my understanding of a semaphore. Let's see what they say about kernel semaphores here. A semaphore is a kernel maintained integer whose value is never permitted to fall below 0. A process can decrease or increase the value of a semaphore. If an attempt is made to decrease the value of a semaphore below 0, then the kernel blocks the operation until the semaphore's value increases to a level that permits the operation to be performed. Alternatively, the process can request a non-blocking operation. When then, instead of blocking, the kernel causes the operation to return immediately with the error indicating that the operation can't be performed immediately. The meaning of a semaphore is determined by the application. A process decrements a semaphore from, say, 1 to 0 in order to reserve exclusive access to some shared resource. That's kind of like a mutex. And after completing work on the resource, increments the semaphore so that the shared resource is released for use by some other process. The use of a binary semaphore, a semaphore whose value is limited to 0 and 1, is common. However, an application that deals with multiple instances of a shared resource would employ a semaphore whose maximum value equals the number of shared resources. Linux provides both systemd semaphore and POSIX semaphores, which have essentially similar functionality. So I guess an example of this would be like a thread pool, where you have, like, say, 10 operating system threads in the thread pool, and you have like a bunch of different, what would you call them? Tasks to perform on those threads. And I guess let me think through this. I guess let's keep it in the vocabulary of operating system threads. If you want to limit the concurrency of a multi-threaded process, so you have like 100 threads running, but 100 threads that exist in the process, and you want only 10 of them to be running at any given time, then you would use a semaphore and have all those 100 threads require the semaphore to be able to run, and then they would then cooperate using that semaphore to determine who's going to be running. I've used that before in concurrent systems where basically, like, you're doing like a bunch of IO with like a server, and it can only handle a certain level of concurrency. And so you want to limit your concurrency, but you also, your programming model, you might not want to express the operations that need to be performed in a way that is very constrained to only having a certain amount of concurrency. So a good example would be spinning up like 100,000 Go routines in a Go program, and then saying, hey, you all have to be limited by a concurrency of 10, so I'll create a semaphore of 10. I wonder if there's a semaphore in the Go standard library. I don't think there is. I guess a channel would be Go's way of doing a semaphore. You would just create a buffered channel with the capacity of however the size of the semaphore. It's interesting that in this book that they talk about semaphores as being an integer, which is really, conceptually, I feel that is like an implementation detail, like an integer decrementing to 0. and not going any further, to me that's an implementation detail. Because everywhere I've encountered semaphores, while it might be implemented that way, there's multiple different ways to implement it. Like I mentioned, channels in Go, they're not implemented as an integer that decrements to 0. So like with a channel, it's a thread safe queue, basically, first in, first out queue. And you can have it be non-buffered or buffered. Not buffered is just a buffer of 0 length. When the channel buffer fills, write operations block. So if you're trying to acquire the semaphore, you're trying to perform a write operation into the channel. And then you would block until there's space for you to acquire a position in the queue or in the channel. You then acquire it, and then you do your work, and at the end you just pop an element off the queue, off the channel. And so that whole thing is not implemented as an integer that goes to 0, but it still would be considered a semaphore. So yeah, I feel like this book is more focused on the implementation in this paragraph. All right, file locks. File locks are a synchronization method explicitly designed to coordinate the actions of multiple processes operating on the same file. Yeah, so this is where you have multiple processes operating the same file. Again, I don't know much about file locks, but I imagine you can lock regions of the file and say I have mutual exclusion on this area, and if the other thread has a separate file description and can seek to a area that's not locked, it can then perform operations on it. That's my guess. And that might be useful for like databases that store data in a single file for a given table, say, but you want to do like row locking. You could say this range where the row is that I'm taking mutual exclusion on it. So file locks are a synchronization method explicitly designed to coordinate action in multiple processes operating on the same file. They can also be used to coordinate access to other shared resources. File locks come in 2 flavors: read shared locks and write exclusive locks. Any number of processes can hold a read lock on the same file or region of file. However, when one process holds a write lock on a file or file region, other processes are prevented from holding either read or write locks in that file. So it's an RW mutex on that file or file region. Linux provides file locking facilities via the flock and fcntl system calls. The flock system call provides a simple locking mechanism, allowing processes to place a shared or an exclusive lock on an entire file. Because of its limited functionality, flock locking facilities are rarely used nowadays. The fcntl system call provides record locking, allowing processes to place multiple read and write locks on different regions of the same file. Mutexes and condition variables. These synchronization facilities are normally used with POSIX threads, as described in Chapter 30. Okay. Mutexes and condition variables. These synchronization facilities are normally used with POSIX threads as described in Chapter 30. Some Unix implementations, including Linux systems with a glibc that provides the nptl threading implementation, also allow mutexes and condition variables to be shared between processes. SUSE3 permits but does not require an implementation to support process sharing mutexes and condition variables. They are not available on all Unix systems and so are not commonly employed for process synchronization. When performing inter-process synchronization, your choice of facility is typically determined by the functional requirements. When coordinating access to a file, file record locking is usually the best choice. Semaphores are often the better choice for coordinating access to other types of shared resource. Communication facilities can also be used for synchronization. For example, in the section 44.3, We show how a pipe can be used to synchronize the actions of a parent process with its children. More generally, any of the data transfer facilities can be used for synchronization. With the synchronization operation taking the form of, sorry, I'm on the wrong page here, taking the form of exchanging messages via the facility. Since kernel 2622, Linux provides an additional non-standard synchronization mechanism via the event FD system call. Ooh, that's cool. This system call call creates an event FD object that has an associated 8-byte unsigned integer maintained by the kernel. The system call returns a file descriptor that refers to the object. Writing an integer to this file descriptor adds that integer to the object's value. A read from the file descriptor blocks if the object value is 0. If an object has a non-zero value, a read returns the value and resets it to 0. In addition, poll, select, and epoll can be used to test if the object has a non-zero value. If it does, the file descriptor indicates as being readable. An application that wishes to use an event FD object for synchronization must first create the object using event FD and then call fork to create the relay process that inherits the file descriptors to the object. For further details, see event FD manual page. That'd be cool with like selecting epoll and poll and stuff. Okay, I'm gonna take a quick bio break here, and then we'll come back and do comparing IPC facilities. Play some music while I'm going here. I thought of something I want to do on the stream here, or off stream, which is to add a BRB message. Oh, pop out my chat. chat here. All right, we're nearing 10 here. I think my meeting's around like 11:45, so I'll probably have to break around like 11:30. All right, continuing onward. Comparing IPC facilities. When it comes to IPC, we face a range of choices that can at first seem bewildering. Oops. In later chapters that describe each IPC facility, we include sections that compare each facility against other similar facilities. In the following pages, we consider a number of general points that may describe the choice of IPC facility. IPC object identification and handles for open objects. In order to access an IPC object, a process must have some means of identifying the object. And once the object has been opened, a process must have some type of handle to refer to the object. Let me reread that. In order to access an IPC object, a process must have some means of identifying the object. And once the object has been opened, the process must have some type of handle to refer to the open object. Table 43.1 summarizes these properties for the various types of IPC facilities. So we got a pipe and a FIFO. Pipe has no name. The handle is a file descriptor. So I've used pipes before. Are FIFOs like named pipes? Here's the Unix domain socket that we're talking about. Are named, is FIFO another word for named pipes? So it's kind of like a character device that you can't seek. Aren't regular pipes also FIFOs? In that they are first in, first out. Yeah, so I like the term name pipe. That's what I've used in the past. It's good to get exposure to some of these other naming conventions, though. But I would call these pipes and named pipes because they both have FIFO semantics. The only difference is one has a path name and one doesn't. Unix domain sockets and internet domain sockets. So Unix domain socket has a path name, yeah. And I think you can do UDP datagram style messaging as well as the like a more TCP like streaming type semantics on it. I'm pretty sure. And inner domain sockets that you of course can do both of those. I'm trying to think. One of these, either name pipes or FIFOs, allows you to read what the process is that sent the message. Which forms of with named pipes and Unix domain sockets, which one allows you to tell what process ID sent the data message, and thus is authenticated as that PID. I think it's the FIFOs, but I'm not sure. Unix domain sockets, okay. FIFO is no way to know the sender's PID from the pipe itself. FIFO is just a byte stream backed by the file system. Once a process opens it, the kernel does not tag reads with "this came from PID X." You can only rely on the file system permissions at open time, not per message attribution, so no sender authentication by PID. However, Unix domain sockets, which are definitely different than internet domain sockets in this regard, you can get the sender PID for stream or datagram AF Unix sockets. The kernel tracks pure credentials. You can obtain them via SO-peer cred, Linux most common, or get pure ID and BICs, or SCM credentials via receive message per message credentials Linux. Okay. Example on Linux. So you got your cred, and yep. Okay. So you get the PID, the user ID, and the group ID, or per message, receive message. Parse the SCM credentials from control messages. Seems like there's a couple ways of getting it. The PID is a kernel asserted, not user supplied, cannot be spoofed. However, PIDs are ephemeral. PID alone is usually not a strong identity. User good is more meaningful. For datagram sockets, credentials are associated with the sending socket, not just the path name. I'm very interested in that because I've ran into this in my career, obviously, where certain projects will use the PID of the sender to authenticate the message, and then talk to the kernel to get more information about the PID, about the process behind the PID, and whereas if you just open up like a TCP connection on the localhost machine, if you bind to like localhost 127.0.0.1 or ::::1, I think it is. If you bind to localhost, then you're not going to get any authentication about what process on the machine actually sent the message or sent the data. So that's where internet domain sockets and Unix domain sockets differ significantly. System v message queue, semaphore, and shared memory. So these all use this concept of a system v IPC key, and then they give back a system v IPC identifier. Then we got postage message queue, semaphores, and shared memory, but the semaphores can be named or unnamed. Unnamed is similar to the pipe, which has no name. This is a POSIX IPC path name. And then shared memory has a file descriptor, interesting. Semaphore has a SEMT. The message queue has a MQDT. I like the file descriptor API, so I guess I'm leaning towards POSIX. Seems a little bit more featureful with having unnamed semaphores as well. But I don't like these identifiers. I like file descriptor APIs. And like path names. Path names and file descriptors. Those are my favorite APIs. Anonymous mapping and memory map file. So anonymous mapping is just some memory mapped. And the memory map file, we say I can memory map this file at this path name. Okay. And then Flock and FCNTL, they both use path name and file descriptors. Okay, functionality. There are functional differences between the various IPC facilities that can be relevant in determining which facility to use. We could begin by summarizing differences between data transfer facilities and shared memory. Data transfer facilities involve read and write operations, with transferred data being consumable by just one reader process. Drink some more of my protein shake here before it gets too late. I must have glitched out my headset because I was muted there. Sorry about that. The one thing that I just highlighted in the book here was the deadlocking on record locks. Sorry, the deadlock detection. I thought that was pretty cool. And I was curious if databases use this, because I know they do some type of like deadlock detection. But yeah. And then down here, there is the record locking, where the record locks get released when the process terminates, which makes sense. And then basically network communication, basically saying like, okay, you have Unix domain and internet domain sockets, and there's little effort switching between the two there. Portability. Most modern Unix implementations support most of the IPC facilities shown in figure 43.1. However, the POSIX IPC facility, message queue semaphores, and shared memory are not quite as widely available as their System V IPC counterparts, especially on older Unix systems. Implementation of POSIX message queues and full support for POSIX semaphores have appeared Linux only in the 2.6 kernel series. Therefore, from a portability point of view, System V IPC may be preferable to POSIX IPC. Yeah, I mean, I've heard of System V IPC more than I have heard of POSIX IPC, to be entirely honest. Let's ask AI here. Which is more popular, System V IPC or POSIX IPC? Okay. Looks sane in 2025. Okay, we're in 2026, bro. System V IPC older is still around. Legacy code, database old daemons, enterprise stuff. Some people like kernel persistent objects. Still heavily used teaching OS concepts. Why people avoid it now. Awkward lifecycle management. Okay, it's good to know. What are the types of namespaces in Linux today? File system, network, etc. So the IPC namespace is System V and POSIX message queues. System V IPC and POSIX message queues. The rest of the POSIX stuff is namespace via mounts. Okay, it's good to know. So it's slightly more compatible with like existing namespace. It didn't need a specific carve out for namespacing, except for the message queues. Okay. System v IPC design issues. The system v IPC facilities were designed independently of the traditional Unix I/O model and consequently suffer a few peculiarities that make their programming interfaces more complicated to use. The corresponding POSIX IPC facilities were designed to address these problems. The following points are of particular note. The system v IPC facilities are connectionless. These facilities provide no notion of a handle, like file descriptor, referring to an open IPC object. In later chapters, we'll sometimes talk of opening a system v IPC object, but this is really just shorthand to describe the process of obtaining an identifier that refers to the object. The kernel does not record the process as having opened the object, unlike other types of IPC objects. This means that the kernel can't maintain a reference count of the number of processes that are currently using an object. Consequently, it can require additional programming effort for an application to be able to know when an object can safely be deleted. The programming interfaces for the system v IPC facilities are inconsistent with the traditional Unix I/O model. They use integer key values and IPC identifiers instead of path names and file descriptors. The programming interfaces are also overly complex. The last point applies particularly to system v semaphores. By contrast, the kernel counts open references for POSIX IPC objects. This simplifies decisions about when an object can be deleted. Furthermore, the POSIX IPC facility provides an interface that is simpler and more consistent with traditional Unix model. Accessibility. The second column of table 23.2 summarizes an important characteristics of each type of IPC object. The permissions scheme that governs which process can access the object. Following list adds some details on the various schemes. For some IPC facilities, FIFOs, and sockets, object names live in file system, and accessibility is determined according to the associated file permissions mask, which specifies permissions for owner, group, and other. Although system v IPC objects don't reside in the file system, each object has an associated permissions mask whose semantics are similar to those for files. A few IPC facilities, pipes, anonymous memory mappings are marked as being accessible by the related processes. Here, related means related via fork. In order for two processes to access the object, one of them must create the object and then call fork. As a consequence of the fork, a child process inherits a handle referring to the object, allowing both processes to share the object. The accessibility of a POSIX unnamed semaphore. Is determined by the accessibility of the shared memory region containing the semaphore. Okay. In order to place a lock on a file, a process must have a file descriptor referring to the file. In practice, it must have permission to open the file. There are no restrictions on accessing, i.e. connecting or sending a datagram to an internet domain socket. If necessary, access controls must be implemented within the application. Accessibility and persistence for various types of IPC facilities. So pipe, these anonymous pipes, only accessible by only related processes, persistent as a process. A name pipe has a permissions mask on the file, and it's persistent to the process that created it, I guess. Unix domain socket is also a process for both. Internet domain socket by any process or anything on the network, really. Systems v message queue semaphores to share memory use a permissions mask, but they're stored in the kernel, not on the file system. They're just part of the objects that are allocated in the kernel. Persistence is kernel. Same thing for POSIX things. The persistence is kernel, but the reference counted. And this concept of ownership and opening them. They also have permissions masked, but they're also file system based. Except for the unnamed semaphore, which has permissions on the underlying memory. Anonymous mapping is only by related process, similar to the anonymous pipe. Memory map file has permissions masked on the file. Persistence is the file system itself. Flock and FCNTL. Permission is opening of the file. And the lifetime is process. Persistence process. The term persistence refers to the lifetime of an IPC object. We refer to the third column of table 43.2. We can distinguish three types of persistence. Process persistence. A process persistent IPC object remains in existence only as long as it is held open by at least one process. If the object is closed, if the object is closed by all the processes, then all kernel resources associated with the object are freed, and any unrelated data is destroyed. Pipes, FIFOs, sockets are example of IPC facilities with the process persistence. A persistence of a FIFO's data is not the same as the persistence of its name. A FIFO has a name in the file system that persists even after all the file descriptors referring to the FIFO have been closed. Kernel persistence. A kernel persistence IPC object sorry, a random thought just occurred to me that if I'm going to be building out larger projects in C, does C follow the same kind of like compilation units as Go? That's one thing that I'm curious about. I think it might. Maybe? I don't know. Because Go creates a .a, an archive file for each package, which effectively is like every Go file in a directory. There's some edge cases there with tests, but basically the Go files that are in a directory get compiled into an archive file. But what's in that archive file? I kind of want to test that out real quick. It's totally unrelated to this chapter, so I'm not going to like add it to the chapter tests here. But I am going to go to chapter 41 because I had some stuff in there, I think. Yeah. mkdir go archive test. CD into there. And I'm going to CD back here and say go mod init as let's echo or just pwd here. So we say go mod init and we'll give it this whole path here. Go mod tidy. Bam. Cool. And then we go under here and there's like this go archive test subdirectory, and here I'm gonna say vim file1.go package is go archive test. Oh, but it has test in it. I'm just gonna call it go archive. CD, oops, sorry. CD back here, mv go archive test to just be, go archive. There we go. Go archive. Vim file1 and we're gonna have func F1, and it's just gonna do like a print of ASDF. Why not? It doesn't need to be used. At least one file in the package should have package comments. Okay. What is complete? Package go archive. I missed that. Package. That's it. Do not use underscore package names. Okay. We'll call it go archive. MV go archive to go archive like that. Okay. Go archive. Oh, sorry. File 1. F1 is unused. Don't care. CP file 1 to file 2 dot go. File 2 dot go has an F2, and then it's also gonna have an import of. We'll just do something like GitHub, or just do like OS, and we'll do a println of OS. Why not? OS dot cheddar. Why not? We'll say F2 here. Then file 1. Say F1. Alright. And we'll say go build. And then l/la of source. Sorry, go pkg mod GitHub cypher0 dev. No, we don't have anything there. And then here cd dot vim main dot go, and we'll say main package main, and we're gonna do a I need my import github.com cypher0 dev go, or actually I'm just gonna read in the go.mod here. Give me my module, then I can just do that, and then I can do go archive. Then here I'll say go archive.f1. I have to capitalize that. Archive f2. Okay, I need to split this. Go to file 1. This needs to be F. And then file 2 needs to be F. Okay. And then if I run my go run main.go, okay, it did print out something. I didn't have a new line, so I need to do printlns in all these. So vim file 1 println, so that we get our output buffering stuff going on. File 2 println. Okay, that would do it. Bam, you got everything now. So now if we ls-la under go pkg mod GitHub Cipher 0dev, no. Go build main.go output test. Sorry. Main.go test. rm test. Alright. So now if I go into my home, or if I find in my home directory dash iname, and I'm going to say star go archive, and then I'm going to say star.a, and 2 goes into devinol. There's no go archive. What the heck? Maybe if I remove .a. Where does go cache.a build files? Definitely put them somewhere. Go env go cache. So lsa dot cache go build. No. Oh yes, why not? Maybe GitHub here. README. Let's cache build artifacts and go build system. Cache, okay. Let's just look under there. Go build the FC. Yeah, these are not what I expected. Module cache is what we're done with modules. Damn it. How do I find the archive for the package I am working on? Which is /go archive. Okay, we'll do our build with -x. Build. We'll do x here. Sorry, doesn't like that. Okay. Here we go. So in here we can say ARL, so L, delete move print files P, ARP, that guy. That is not an AR file. We'll do file on this, or sorry, type on this. Wait a minute. No, it is file. Current AR archive. PKGA. Okay, let's redo our build. Kill, kill, kill. RM test. We'll do our build again. With the X. He said there's a cat. Work B something or other. .a. I don't see any .a's here. Mod info. grep cat. That's only. Why did that? I got rid of standard error maybe. Okay. Work. Can I CD into here? Does this still exist? No. Let's do grep.a. Grep.a. Go clean cache, mod cache, fuzz cache, everything. So now if I ls-la under that cache, go build. Huh. Thought that would clear that out. Okay, let's try this again. Okay, now we got a bunch of .a's. Nice. Okie dokie. Wow, there's something going on with my computer right now. It's taken off. Huh. Maybe that was my workstation humming along. I think it was because I cleared my cache. We do this btop. I'm gonna do this. Go build x and then pipe this into my build log. Oh, damn it. Clean. Let's say 2 and 1. No, I have to do 2 and 1 here, right? 2 and 1. There we go. Okay. Let's vim our build log and see if we can find our .a's. Let's look for go archive. Oops. What I'm gonna do, I'm gonna kill that. I'm gonna full screen this. Do it like that. No, I like that better. So we're going to cat out our build log and we're going to grep for go archive because I want to see where this archive went. So it went to this B002. It said pack these two things. Let's see what it's actually running here. So it's saying, hey, use the compile tool, which is, I think, the compiler. The output is going to be the package A file. We're going to trim this path. The package is going to be this. I think that's what P is. Build ID is this. Go version is this. Concurrency, no local imports, import config, pack in these files. Okay. So I think what I can do is search for this now. So it's kind of like the identifier. Either this guy is the identifier or this guy. If I grep for that, it should tell me where that file is going. So it did a CP into this cached D file. Okay. So if we say ARP now on this, this should give us, I know it's giving us a lot of garbage. Go object, build ID, and then a bunch of binary, clear, sorry, man, AR. Delete, print the specified members of the archive. Display a table listing the contents. That's what I want T. ART, that guy. So they're just a single Go object file. So it doesn't create separate object files per file. It just has a single object file. What I'm going to do now is I'm going to go under my cache Go build and just tree out everything. I don't have tree. LT? No. What I need to do is find. Find dot type file, and we're going to say while read line do something done. The something we're going to do is we're going to say if I might just be able to guard this by saying like test, or we're going to run, no, that won't work. Let's just run ART on $line. Interesting. File format not recognizing a lot of them. Most of them just have Go. This guy has like multiple object files because it has a test and a stub. It looks like it just goes to this one here. Some of them have multiple object files. But if I take, yeah. It's interesting. I like to play around with that more in the future, but it seems like by default, if you have multiple files in your package, it just throws them all in one object file. But there is a mechanism to have multiple object files. I wonder if I create a test, go back here, go into Go archive and say, hey, vim pkg test.go package go archive underscore test, and here we're going to say like func test foo, and it's going to have like I don't think I need to do my imports because I can just say testing.t here, which is a T like that, I think, a pointer to testing.t, I think. Yeah, and then here we say t.fail. and give it a message. Fail now. Fail now. Was not fail now. It's what is the one that you can, I guess, fatal? Yeah. Fatal. Now? Fatal F? What do you say fatal? Blah, 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 blah. And we're going to go test, and I'll fail the test. And then if I go back over to here, it's not going to need to compile that into the archive because it's a test. And tests are just compiled in different objects. Huh. I wonder how it does its content addressing. Does it like hash together the files of the package? Not sure. Okay. Something to explore for a later time. It is (10:51). Let me make sure that I'm not going to be too late for my meeting today. Okay, I got about an hour. It's 11:45 is the start of my meeting. So kill this. Get status. cd.dot get status. Get add chapter 41. Actually, go under chapter 41. Let's clean up some stuff here. rm test. Get status. Get rm build log. Get status. I got my mod, my archive, my main, progress. Get add dot. Get or cd backpack. Get status. Get DC. F1, F2. Add test of how Go compiles archives. Okay, foreground. Let's continue on. We're almost done with this chapter, so we'll finish that up and I might just take a break. Okay, so we got kernel persistence. A kernel persistent IPC object exists under either exists until either is explicitly deleted by or the system is shut down. The lifetime of the object is independent of whether any process holds the object open. This means that, for example, one process can create an object, write to it, and then close it or terminate. At a later point, another process can open the object and read from the data. Examples of facilities with kernel persistence are system v IPC and POSIX IPC. We exploit this property in the example programs that we present when describing these facilities in later chapters. For each facility, we implement separate programs that create an object, delete an object, and perform communication for synchronization. File system persistence. An IPC object with file system persistence retains its information even when the system is rebooted. The object exists until it is explicitly deleted. The only type of IPC object that demonstrates file system persistence is shared memory based on a memory map file. Performance. In some circumstances, different IPC facilities may show notable differences in performance. However, in later chapters, we generally refrain from making performance comparisons for the following reasons. The performance of an IPC facility may not be a significant factor in the overall performance of an application, and it may not be the only factor in determining the choice of an IPC facility. The relative performance of various IPC facilities may vary across Unix implementations or between different versions of the Linux kernel. Most importantly, the performance of an IPC facility will vary depending on the precise manner and environment in which it is used. Relevant factors include the size of the data units exchanged in each IPC operation, the amount of unrelated unread data that may be outstanding on the IPC facility, whether or not a process context switch is required for each unit of data exchange and other load on the system. If IPC performance is crucial, there is no substitute for application-specific benchmarks. Run under an environment that matches the target system. To this end, it may be worth writing an abstract software layer that hides details of the IPC facility from the application, and then testing performance when different IPC facilities are substituted underneath the abstract layer. Summary. In this chapter, we provide an overview of various facilities that processes and threads can use to communicate with one another and to synchronize their actions. Among the communication facilities provided on Linux are pipes, FIFO sockets, message queues, and shared memory. Synchronization facilities provided on Linux include semaphores and file locks. In many cases, we have a choice of several possible techniques for communicating and synchronization when performing a given task. In the course of this chapter, we compare the different techniques in various ways with the aim of highlighting some differences that may influence the choice of one technique over another. In the following chapters, we go into each of the communication and synchronization facilities in much more detail. Exercises. Write a program that measures the bandwidth provided by pipes. Okay. Since we're at the end of the chapter and I have like 45 minutes to kill, or at least 30 minutes to kill, I'm going to record here 887, and we'll say that is at 10:57, and then I'm going to do some exercises here. MKDR on chapter 43. Okay. All right. As command line arguments are, we should accept a number of data blocks to be sent. So you accept size of each data block size 2, 3. After creating a pipe, create pipe. Fork a child. Child writes data blocks to pipe. Parent reads data blocks from pipe. Parent prints elapsed time and bandwidth bytes per second. FD2. So we have a reader and writer in here. We fork, we assert our PID is greater than or equal to 0. We'll say greater than 2. Because 0, 1, and 2 should definitely be... Oh no. You can't do this. This will crash. Greater than or equal to 0. Okay, that means no error. Okay, I understand what it's doing there. Pit is equal to 0, then it's a child, in which case we close the read end. And for m blocks, we write our buffer. So we have to go into the while to write our buffer. Once you've written our buffer n blocks times, then we close the write end and we exit success. And then we close our FD1 because we're reading. We then start the clock, and I feel like we should do that up here. I guess it's fine. Our fork, we're just gonna jump or do a conditional branch here, close the file descriptor and start the clock. I'm gonna start the clock up here. Then we go through our n blocks, and then we read our block, and we then do our get time, close our file descriptor. I wouldn't say that opening and closing file descriptors is part of the maybe it's right. Maybe we shouldn't do that. Okay. Status, then we wait and assert that it exited, and then we compute our diff, and then we say, hey, your bytes were this, your bandwidth was bytes per elapsed, and we print that all out here. These are all in doubles, and then we free up our buffer and exit. We don't need to do this free because we're exiting. Alright, pretty good. It's pretty good code quality there. We'll say we'll do 43. And here, I'm just going to RM exercises, self join, test, make clean, and clang D. We can delete that. Get ignore, getting rid of that. Sig cache, don't need that. RM build.zig, then make file zig. Okay. Don't want any of these as well. Do make, build, measure pipes. Yep. So I'm gonna say 10,000, 10,000. $100,000. So if the first argument is, if I look at my measure pipes, so that's going to be first argument is number of blocks. So I'm going to say 10,000 of like a gig, right? So you have here, that's 10,000, 100,000, 1 million, 10 million, 100 million, 1 gig. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And we do maybe 100 of those, 100 gigs. Or maybe just do 1 gig. We'll do 10 gigs. Okay, that one's not working. Sorry. 1, 2, 3, 1, 2, 3. There we go. So that's 6, 5. If I take 1 away from here and add it to here, that's 8. Write me shell that invokes this program such as sorry, boom 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 10 1 2 3 4 5 6 7 8 9. And then we do 1 less 0 here, and we add a 0 here. One less 0 here, add a 0 here. Dot dot dot, and so on. Make it super simple expression, maybe like 3, 1, 2, 4 lines max. Huh. Why did it put that there? We need to echo out our parameters too. So we say do echo $n and whatever the hell this is. I'll just copy all this. There we go. So it's going to 100, so we just need to increase this thing up here. Say 1 0 0 0 0 0 0 and 1 0 0 0 0 0 0 0 and 1 0 0 0 0 0 0 0 0. 1 2 3 4 5 6 7 8 9. 1 2 3 4 5 6 7. So I need to 8. 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7. 1 2 3 4 5 6. I'm gonna take this last one off because I think that was not performing at all. Yeah, we'll do that. 2.3. Run.sh. Okay. Repeat the preceding exercise for systemv message queues, POSIX message queues, Unix domain stream sockets, and Unix domain datagram sockets. Use these programs to compare the relative performance of various IPC facilities on Linux. If you have access to other Unix implementations, perform the same comparisons on those systems. Alright, we got time to do that. So I'm gonna trash results and build up this run. So this is gonna be measure pipes. Vim run. So this is going to be going into we'll do mkdir-p results, and then here is going to go into results slash pipes.txt, and then what I'm going to say here is, hey, copy, give it this guy, given this program, rewrite it to use systemv message queues. Queues. Boom, boom, boom. Okay. Copy code here. Then measure sysv mqs. MSGQ. See. Let's review it. Okay. Same helper function. I'm gonna grab this guy and say vim helpers.inc. This guy is gonna need some definitions here. If we do, actually we don't need that. We'll just say that. And then if we vim up measure pipes, let's see, we can delete this and say helpers.inc. Get rid of that and go over to here to sysv and do the same thing here. Say debang helpers.inc. That. Normally I try extracting some of this stuff, but yeah, I don't really care to do that now. I think this needs to be dot slash like that. Put it down here. Why is it saying that? Struct time spec? Helpers Inc. Okay. That's why I put it down here, dumbass. Assert standardized standard lib string sys wait time. Oh, why is it putting it up there? Okay, I need to put it like that, and it'll respect it. Okay. Okay, so I can get rid of this. Okay, we're gonna, oops, bring it back here. So here's where we kind of fork off. It's where we create the message queues. So this is just calling pipe. This is calling message get, IPC private. IPC create was 600 to get this message ID. We do assertion. And then we got our time spec start and end. We then fork our PID. There's gotta be a way that we can share code here. So the stuff that's different here is the creation of this. A lot of the stuff in the inside is different because it's just totally different the way that we read off of the different things. Do we need to do this malloc? size of message buff. So we allocate our buffer up here, and then this buffer, we do a memcop into the buffer mtext. What, can we just point to it? Instead of doing a mem copy in the child mcpy, why not just set the pointer to point to buff? This is wrong. Okay, we don't need to free these. Okay. So now we say make, and our runner is going to do the same thing, except it's going to try to do it. I don't know if it's going to be successful, but it's going to say measure sysv message queues. It's going to be sysv msg queues, and we'll do our run. Actually, oops. Then run. We're going to T this into there. Okay. And we'll do a run. So we get 2. We can play with the size and get it down to like less than a second, and then it starts going up with very small sizes up to like 9 seconds. So it's about 2. Then we get invalid arguments. Immediately it stops working. Okay. Well, let's try running it manually. We're running build, measure, sysv. We'll just do like 1010. Yeah, that works. We'll say 10,100. Invalid argument. Okay. 100, 100. 100, 1000. 10,000 is too big. So alright, so it's saying undeclare Lmax. What the frick is this? Well, let's cat it out. Proxys kernel message max. Alright, so it's 8,000. Alright, we'll do this instead. Then measure sysv. So we open that for reading, we assert FD is greater than 0, 1, 2, greater than 2. Don't care about all that. Then here we do the inverse assert that n is greater than or equal to 0. So we say, hey, you got a character buffer. Then you're going to read and close it. Stir too long, message max. So we get our message max out here. And then we say if block size greater than message max, then we're done. Okay. Make, and then we're gonna say this guy should error out. Yep. So I can only do 8,192, and let's try doing a bunch there. Alright, let's try running it. So these first ones are just going to error out. This one's going to take about 9-10 seconds. And then we'll see some of these message queues erroring out. About 2 seconds. Okay. And then we said POSIX message queues, Unix domain stream sockets, and Unix domain datagram sockets. So I'll do this one again. Cat out measure pipes into Wayland copy. Rewrite this program to use POSIX message queues. Avoid allocations inside. Allocate memory up front. Avoid needless allocations of messages in the child. What's interesting is it gives you this problem to do, and it hasn't even shown us any code yet. It's like, yeah, just do the exercise, you'll figure it out. I mean, nowadays we got AI that can just write all the code for us, but it is funny they didn't really prepare us for this exercise. So this would be measure. This would be POSIX message queues. POSIX sgqs.c. Paste that in here, and we're gonna get rid. Get up here. Get rid of this guy. Get rid of that. Write it out. We're then going to allocate a block. Send receiving. Create a POSIX message queue this time. We're then gonna open it. This is gonna be a message queue with a named. Let's go back to the table here. POSIX message queues. I have a POSIX IPC path name, yeah, and to give you a MQDT. Yep. Message queue data type. I'm just gonna assert. I don't like doing all these conditional branches. So MQ is equal to, we'll just call this not equal to, and then okay, so we have our thing opened up. MQ name is measure MQ. I don't think I'll have the permissions to do that, so I'm going to do it under temp. And then, so we say, hey, get adder, actual adder. Okay. So we do our fork, we send, and then we do all of our receives, and then we do the same waiting, closing of stuff, calculating of results, and exiting. Okay. So let's go ahead and measure that. Vim run. So we'll do the same exact loop. This is going to be measure POSIX. message queues, POSIX. Okay. And then let's go and run. And yeah, I'll let it run. Why not? Just takes a few seconds. I think this will be the last one until I come back. I still have to do the Unix stream sockets and Unix datagram sockets. I didn't build it. Build. Make. If I do build, measure POSIX, message queues 1010. So that had an assertion failure. Measure POSIX, message queues. I changed this to an assertion. No, not that one. This one here. It does its message queue open. And so say if message queue is equal to that, then say, hey, P error. Okay, we'll do it. We'll do it. We don't have to assert everything. Make. Oops. Permission denied. Okay. We'll do a local file then. We'll do under build. We'll put under build. Measure POSIX. We'll say, hey, you belong under build. Measure MQ. Invalid argument. Man MQ open. MQ overview. Oh, it's not a file system thing. Okay. Measure POSIX. So they're right. Measure MQ. Make. Okay. And I'm going to say, hey, run. You guys don't need to run now. We'll just run the one that we care about. Kill, run. That's similar to the other message queues. So far, the name pipes are like the most performant. All right, I'm going to leave it there because I have a meeting to go to, but I'll be back on in a couple of hours this afternoon. It's probably going to be a while because I have to go to my meeting, I have to eat lunch, I have to do my cardio, and I have to do some off-stream work. So probably won't be until mid to late afternoon today. But when I get back on, we'll measure the performance of Unix domain stream sockets and Unix domain datagram sockets. And we will continue on with pipes and FIFOs. Cool. All right. I'll be on later today.